Greg.
Well, hello, good morning. I'm Greg. I am I just graduated from CSU, computer science, as Martin said. I've been working with Martin for a few years, so Python is kind of everything that I do in Martin's group. So I'm excited to teach some of it to you guys today. Quick show of hands. I know you guys just took that survey, but for my own reference, are you all undergrads? Anybody not an undergrad? Okay. Okay, a couple. How about Python experience? Anybody particularly fluent with Python, expecting a boring lecture? Okay, cool. All right, well, in that case, we're going to get into what is kind of the quintessential first thing you learn when you learn a new programming language, which is to write a program that prints hello world out to your console. So at the risk of sounding condescending, if you don't know what hello world is, what printing is, it's just putting text out on the console. That's all printing means.
Why don't you walk them through how they're going to log in and stuff like that?
Oh, sorry, are you guys on your clusters? I'm not sure how far in.
So, yeah, why don't you walk them through how to log into the cluster, because that's where they're going to be running these.
Oh, I'm sorry, I thought that was before this. Okay, cool.
No, you need to go through a terminal.
Oh, gotcha. SSH.
Oh, no, it is typing. I just.
Okay, so
Have you
just,
done it the year before? Because you can click on it, right?
so,
Yeah, it looks like a weapon.
yeah, that's what, okay, so just SSH into it?
Yeah.
All right, so yeah, you're going to SSH. This is the command you're going to use.
Oh, gosh.
You probably have a different username than this. Oh, yeah, this is probably just one you get. But yeah, if this is not you, just switch out your username with what your username is, so you can get onto the cluster. And the cluster is what we're going to be running Python on.
And then that, you just type in. It doesn't show the dots, but it's typing.
Okay, yeah.
Is anybody struggling with this at all?
Yeah, give me a few minutes. How you're on it. Arnold, what about you?
Are you on?
You're on the EID.
Switch it to the CSU.
Oh, I have a
So
E
what
bar.
the rest of it is, I get to the language learner, but then I also went back to your, like, you can go back to the author you guys have on the CD. Basically, everything.
So I'm just gonna cancel out
Yeah.
and
I
rerun
went
it.
to, the
So now you can just put your password.
I went down like 2 or 3 steps, go back up, I'm just gonna go exactly where.
All right.
So everyone has logged in, is that right? If you have not, please raise your hand. Oh, where's that?
Good.
You probably misspelled it or something.
Yeah. It's kind of hard to spell my last name, though, so I'm
Hold on.
kind of confused. I was never actually.
Oh, your login.
Oh.
You
Oh, you have to write in
Your-
username?
Yeah,
Or-
it's just,
Okay, gotcha.
okay, so, yeah, and then,
So it's just like,
yeah.
okay, so it's like whatever.
Yeah. Okay.
Okay.
Yes,
You're in?
I'm in. It was because somehow I got the wrong username and
Yeah,
cut and
sure.
pasted.
Okay, so could you go back to the other thing? So
Yeah.
for people who are using Macs, or I guess maybe also whatever program Arnold is using, but in a Mac you'll type SSH, which is the command that you want to run, and then here is your username at the address of the computer. So whatever username I sent you is what goes in front of here. If you don't type anything, it defaults to whatever your username on that computer is.
If you don't type anything, it will ask you.
What?
This is the way.
I think Macs usually default to whatever is on there. But in any case, it depends on the particular software. So that's, once you do that, you're not going to do this because this is Hayden's.
Yeah.
Go to the account now. So you will then go to the home directory. Just see. So you will be defaulted into your home directory, and so you should have something that looks like this as the command line. Is everyone like? Except obviously it should be a different username. There might be some slightly different formatting. Does everyone have something that looks like this? This is at my username at login1. This means I'm actually logged into the cluster. So you're not, anything you type in here is being shipped off to the cluster, that command is running, and the output is going back locally. So the execution of the command that you now type is not done locally on your machine there, but sent to the cluster and then shipped back. Okay? That's what we want because we want to try to have you all run on a relatively uniform operating system because how you interact with Python is different on a Windows machine, different on a Linux machine, different on a Mac OS. So for today, that's the reason that we're logging into the cluster. For the future, the cluster also has 600 compute cores on it and a bunch of GPUs and stuff like that. So we will use those computing resources to run simulations and do calculations. It's important down the line, but today we just wanted it as a uniform operating system platform for everybody to run Python on. You can, in your own time, figure out how to run Python locally. So that Python XY link I sent out to you, you can run all of these programs, these Python programs that we're going to do today, you can run them on your own machine locally with no internet connection or nothing. But we didn't want to deal with troubleshooting with different operating systems today. Any questions on that?
I just have dash.
Yeah, so
4.1.
yours, I
If I'm just in a
updated.
different place, that's totally fine.
I can change it. I updated their bash RC and I did not update yours to do that. But I can do that right now, actually.
Okay, it doesn't matter. I can live.
It'll matter in a second.
Oh, okay. Well, then maybe you should fix it.
Yeah, I will. It will matter in a second because I've aliased Python. Okay, so go ahead. Why don't we put it back in full screen?
Cool. So, right. So, just to give you a quick kind of glossing over of a couple of important Linux commands that you want to know in case you don't know them. CD is how you get around in your directories. If you think of Windows Explorer, you just double click on folders and you can go from folder to folder directory, things like that. CD is how you do that in command line. So, for instance, right now I'm in the home directory. So if I want to go into see this blue day one folder up here, that's where our files for today are going to be. So I'm just going to do cd day one, and then I'll hit enter, and then you'll see my little text off to the left that tells me where I am. Says now I'm in day one. All right. So when I'm in a new directory, generally the first thing I want to do is type ls to see what else I have in that directory. So I go into day one, I see that I have 3 folders in there. One of them is called Hello World. Let's go into that one.
And if there's ever any issues, if he's going too fast or something.
Yeah, please. I'll glance up as often as I can. Just raise your hand or call out my name or something. Okay, so I've CD'd into Hello World. Is everybody with me there? All right, so go into V1. That's where we'll start at. And then you'll see if you ls inside the V1 folder, you'll probably see these 2 things, helloworld.py and then helloworld.py with a little tilde thing. Don't worry about the thing with the tilde on the end. That doesn't matter right now. So now we're going to use a program called vi. So if you type vi and then helloworld.py and then hit enter, you should get this. So VI is a text editor. It's like Notepad or Word, or it's not as sophisticated as those, but it's been around for as long as computers have been around. And you can. The main benefit that I've noticed of using VI is that you can edit text on a machine different than the machine you're sitting at right now. So, for instance, we're all using VI to edit this text file that's on the cluster. We're not even sitting in front of it, so that can be handy, as you'll find out soon. So Python is notorious for being, well, maybe notorious is the wrong word, but it's known for being very user-friendly. And in this case, this is a good example of why, because in order to write a full Python program, all we need are these 2 lines of code. So for instance, I'm going to introduce you to a couple of terms. please raise your hand and stop me if I'm going too quickly. But we're going to use a variable. And a variable in Python is, you can think of it as just a box that holds some data that you want to access later. So our variable is going to be called hello world. This white text up on the left is the name of our variable. And then there's some text in between quotes over there that says hello world in red. You notice that the capitalization and the spacing is a little bit different, but you'll see what that's about in a second. This hello world is just the name of the variable. That's what we have to type in when we want to access the information in that box later on. And print is just a Python command to take whatever is in hello world and paste it out to the screen. You can think of it that way. So all we're doing here is taking the text hello world, we're putting it in a box called hello world, and then we're calling print on that, on that variable. So what happens when we run that? Oh, I'm sorry, that was way too fast. Here, let me show you how to get out of it. So when you're in here, this is, you're in here, your text editor. I'll get into how to use this in a minute, but for now, type :Q, and then hit enter. Okay, is everybody out of it now? Anybody run into anything? All right, so type Python hello world.py, and then hit enter. And you'll see that it took what was in those quotes and it just printed it out to the console. So pretty straightforward, not reinventing the iPhone here, but it's pretty useful down the road to be able to store things into variables and access them later on. So if you remember how to do vi hello world.py to go back into this text editor, and then you want to use your arrow keys to navigate this cursor around. So once you find your cursor, navigate it into this hello world text, and I'll show you how to edit a text file in a second. So is everybody kind of right here at the end of this text? Not yet? All right. So once you get here, hit the I key, and you'll see at the bottom, it changes it into insert mode. You'll see that insert. That means you can start typing things into this file, and it'll change it. So for instance, if I want to, backspace out world and say hello Fixman class, something like that, type in whatever you want. Once you're done typing, you hit escape to go out of insert mode. So that means you won't be putting new characters in. It's just taking kind of commands from you now. So once you type in some text into this little text, variable, you can put whatever you want in there really. So you'll do your colon again. That means you're getting ready to give the text editor a command, and then you'll do WQ. And the W, you remember the Q before, that means quit. The W means write. So :WQ means save and quit, basically. Is that clear? Okay, so :WQ, whoops. Read only option, oh, yeah, that's true. Okay, this file is read-only, which means we don't have permission to edit it, I think. Let me see if, hey Martin, some of these files are read-only. Is it okay if I change them to? Sure. Okay. I don't know why. Permissions to change stuff.
It's not read only.
Oh, yours isn't read
Yeah,
only?
because I just changed it.
Okay,
so-
if you can, yeah, if you can.
I can do it. I'll see.
Okay, yeah, if you guys can do it, then if it works for you, that's fine. So once you've saved it and closed it out, do Python hello world.py again and run it and see, you'll see that it displays the changes that you made. Okay.
No, just do ls.
LS?
Okay. You should be able to edit it now. For some reason, I had it saved as you.
Oh, it's okay. All right, cool. So let's do cd, and then you'll see that I type // That means whatever folder I'm in, go back one. So I'll do an ls just to kind of get the bearings. And then I'm going to go into CDV2.
Yeah, that.
You'll see that we have another hello world thing in here. So I'm going to VI into it. I know I'm going kind of quickly here. Is everybody with me? No? That's all right. Anybody need me to backtrack a little?
So is Hello World a file or a directory? Sorry, we didn't.
Okay, yeah, that's a fair point. There's multiple things called Hello World right now. Hello World is a directory which contains a file called Hello World, which prints out Hello World. So that is a little redundant. I'll grant you that. If anything, if that's, if you need me to go back over that, I'm happy to. This here is the name of the file. So it's hello_world. Up there is the variable called hello world. That's the text. So yeah, it all says the same thing. It's supposed to try and illustrate just taking data from a variable and printing it out. So if anything is lost, let me know. So are we all VI? Are we all on VI with the new hello world thing? Okay, cool. So what we're going to do with this is to look at how to do something multiple times. Because say for instance that I wanted to print out hello world 10 times. In what you'll be doing within molecular analysis or molecular dynamics, you're going to be doing a lot of things iteratively, and you don't want to manually tell it to do it every single time. So it's handy to have some sort of structure that lets you loop through things as many times as you need to. So you see up here we have this variable called hello world again. You should be familiar with that now. We also have another variable called max iter. That just means maximum iterations. You can think of it that way, and it's just set to the number 10. In Python, you can store any kind of information in any kind of variable. You can put text or integers or whatever you like into variables, and it's easy that way. This loop up here that says for I in range max iter. So I'm going to start from the right and kind of work to the left and explain a little bit. Range max iter takes max iter, which is 10. All right, and basically you can think of it as a number line that goes from 0 to 9. It doesn't go up to 10. It goes, in Python it goes from 0 to 1 less than 10. If that's confusing, I can get into it some more. But generally, when you do a range to a number, it starts at 0 and it goes up till right before that number. So from here, we're going from 0 to 9. So this for loop, your I, this I is another variable. And it's just going to hold whatever number you're currently on. So when you're looping from 0 to 9, I is going to start at 0. Then it's going to be 1. Then it's going to be 2. And it's going to continue on until it's 9. Max iter is going to stay the same value the whole time. So when you do print I plus 1 hello world, that's just going to print those two variables out to your screen. So I'll show you what that looks like. You should follow along with me. So do :Q to get out of VI. And then do Python hello world. And you'll see that it prints out that I value. Although if you noticed in the script it said I plus 1, so the reason this doesn't start at 0, like I said, is because it just says I plus 1. And then it just iterates through that 10 times. Now if you will follow me back into vi hello world.py, and we're going to change max iter to another value. I'm going to change mine to 15. Feel free to go nuts if you want to, but don't put it. I wouldn't suggest putting it over 100. All right. So, is anybody unfamiliar with editing text files? I can go back over that if you need. All right. So what I did was I was in VI with my hello world. I hit I to go into insert mode. I changed max iter to 15, and then I just did :WQ for write quit it. Okay, so that's what my hello world looks like, and then when I run it, now I get it 15 times instead of 10. So you can imagine that when you're doing molecular dynamics and you need to do something in an iterative fashion, this is a really handy tool to be able to have to set a number of times that you want to iterate through something and have it do exactly that. Okay, now I'm gonna do any questions before I move on. Okay, I'm gonna do cd dot dot so that I'm back in this directory. And then I'm gonna go into v3. We're gonna do a couple more just to increase some familiarity with this. So vi into hello world again for v3, and we're gonna look at let's see here.
It's a reading unit.
Right, giving commands from the command line when you're starting. Okay. This one, I think it might be better to have you run it, and then I'll explain it. So follow along with what I do. Just do Python hello world pi, and then do a 3 or some small number. Yes.
Can I get back to this again?
Colon Q.
After insert?
Oh, escape colon Q.
Is there?
Did you
No,
edit?
right, send slash change.
Hit colon Q's
Exclamation
exclamation
mark.
mark. Yeah, so that means save without, or quit without saving. So you made some change, and if you want to save it, you put WQ, right, to quit. If you don't want to save it, it's a Q's exclamation.
That took a second to run. I'm guessing the cluster is doing other things, but yeah. So when you run Python hello world 3, it prints out hello world 3 times. So I'm sure you can surmise that this code takes a user input value. You know, in this case, it was the number 3, and it just prints out the text that many times. So we'll look at how it does that now. This this part here, it says int sys.argv1. It looks very convoluted, but all it really means is sys.argv1 is just that three that I typed in after I typed Python hello world. It just takes that next input that I typed and it saves it as an integer. That's what this int means. And then it takes that value and puts it in max iter. Okay, I realize that's kind of a lot to digest. Is that okay for now? So we've got the input that's typed in at the command line when we first run our program. It's not, that value 3 isn't saved in our code anywhere here. It's given by the user. Okay, so it gets saved in as a variable after this program starts, and then it just iterates that many times. I'm going to go into v4 now. So I do cd dot dot to go back into this hello world directory, cd v4. And then I use vi to open hello world again. Now, when we iterate over things, sometimes we want to iterate a certain number of times, but we don't want to perform an action every single time we iterate. And there are a variety of reasons why you might do this, but I'm going to show you how to do that for now. You're probably pretty familiar with this by now, but I want to draw your attention to a couple of things. First is this percent sign. So you're familiar now with this for I in range max iter that that just iterates through 10 times. This if I %2, what that means, I %2 is modulo is the word, but it just means remainder is the way you can think of it. So if you do a division of I by 2, if you do I divided by 2, sometimes you'll get 1, sometimes you'll get 0 for these values from 0 to 10. Okay, so we're starting at 0, for instance. If I do 0 divided by 2, I'm going to get a 0. If I do, I'm going to get 0 with a remainder of 0. If I do 1 divided by 2, I'm going to get 0 with a remainder of 1. Okay, so this percent is looking at that remainder. And this double equal sign is, it's Python's way of saying, is this true? So what this is asking is, if I take I and I do a modulo by 2, is that number 0? So 0 divided by 2 is 0 with a remainder of 0. So that's true. I realize, I think that didn't make sense coming out of my mouth, but does that make sense at all? Raise your hand if you're confused. Cool. Where are you hung up?
So I just didn't get to here. I'm in P3.
Oh,
And now we're into the, and we'll walk off.
oh, we're in B4 right now, so go back. Sorry, I know I'm moving a little bit quickly. We just have some other things to get to. Okay, so does modulo and the double equal sign make sense? All right. So I'm going to run it and just show you guys that it does what I claim it does. Right, so in this case, it's comparing that I with dividing it by 2, looking at the remainder and deciding if that remainder is equal to 0 or not. And when that remainder is equal to 0, it prints out this text. So it's iterating through 10 times, just like the last couple examples, but in this case, it's only performing an action when I is odd, for instance. Okay?
Greg, before you move on,
Yes.
2 things. One, can you reinforce the idea of the if statement? I think that was the point of this, more so than modulus.
Oh, yeah.
And then you could also print out the modulus at every step to show what it is equal to.
Oh, okay, sure. Yeah, that's a good point. Yeah. This if line up here is a very powerful thing in Python. You'll get to like it a lot. It lets you specify a condition like this where maybe you don't want to just compare 2 numbers together. Maybe you want to take 2 variables that you have and see if they're equal to each other after you've done some sort of analysis. So this if statement lets you do that. So if you want to check that something is true or false or any number of other things before you perform some perhaps computationally intensive action, you can do this if statement. With for loops and with if statements, you have to end them with these colons on the end, or they'll complain in kind of a vague, hard to understand way. So yeah, just put colons on the end of your for loops and your if statements, and you won't run into that issue. But yeah, being able to use these if statements to make comparisons between your variables is.
And what about being tabbed in and then else statements, or what gets executed and what doesn't?
Right. So yeah, I'll add a couple things here. You're welcome to follow along with me. If you do, please try and follow along. Try and watch what I'm doing up here, because I'm going to add a couple of prints here and just show you what I mean by this. So I'm interested in this case if the remainder of I divided by 2 is 0, and I want to print something out, right? But perhaps I'm interested in something else if that's not the case. So if this isn't true, if I modulus 2 isn't 0, I can do this. I can do else. Another thing you'll notice Martin just pointed out, I have these paths here. These are very important to kind of the structure of your Python code. It's how Python knows how your code is structured. So you can't have. Let me think about how I want to say this. When you start a for loop, you have to tab everything that you want to be within that loop. So everything that I want to happen 10 times, I need to have tabbed after this for loop. Let me explain. Let me clarify that a little more. And, Okay, so what I've done here is this. It checks to see if this is true, and if it's not, it does this. It'll print else, and it'll run through this loop the 10 times that it's been doing how we've shown, and then once that loop is done, then it's going to get to this next block that's not indented. Does that make sense? Kind of structure. So, and likewise, everything that you want to happen as a result of this if statement, you need to have it tabbed again. So if I wanted to print 100 other things, I would have 100 more print statements after this, or maybe I would use another loop. But just to show you for now.
And it's requiring a tab, not an equivalent number of spaces.
If you use an equivalent number of spaces, you have to do it consistently. You can use spaces, but you have to do it. You have to pick one or the other, and you have to be consistent, or it'll complain at you. Okay, so I'm going to do colon.
Convention.
Yeah.
Well, you can look at it, you just can't
Yeah, exactly.
do anything with it.
So I'm going to do :WQ to write and quit. And then I'm going to execute it by doing Python hello world.py. And you'll see it did what it did last time, where it prints the odd numbered hello worlds, but in the case where I is not odd, it prints else instead. And then after that loop is done, you notice that it does the...
Be careful, it's printing I plus 1.
Oh, you're right. Yeah, I'm sorry. It's technically the even numbered i's that it's... So this, what Martin's talking about is this right, this right here. This right here where it says I plus 1. So technically when I is 0, it's printing a 1. That's why that happens. Okay.
Could we do one more thing?
I would love to.
We'll go back in and tab in the end.
Print the end.
Yeah.
Oh yeah, good point. So if I don't do this correctly and I leave this tabbed in like this, anybody want to take a guess at what would happen?
Print the end every time.
Print the end 10 times, right?
No.
Right. Usually I can type. All right. Does that make sense why that happens? Okay, great. We're going to cd ... a couple of times till we get back to this directory, the day 1 folder. We're going to go into, let me look real quick.
I can do a data set.
Right. Okay. Go into the data set folder. And then you're going to want to go into, I think you want to go into trajectory first. Okay. Now for this, is VMD on the cluster? I don't think they can run
You
it.
can't run it remotely.
Yeah. Okay, so for this part, you're just going to watch what I do.
Or if you have VMD remotely and you download these files, or locally and you download these files, you can follow along. But if not, don't worry about it. We'll get to it later.
Is everybody with me?
Day one and what
You
should be
hit PWD.
Do PWD.
That's on YouTube.
Oh, me. The little back one? Yeah, CD .. And it doesn't have day 1 now, so do LS.
No.
So now go into data set.
Whatever you want.
How are you doing it so fast?
Oh, is it tab?
Tab.
Do D, type D, and then tab. Yeah, that's a handy trick if you guys are interested in how I'm doing some of this so quickly. For instance, if I want to go into the trajectory folder, but I don't want to type the word trajectory, you can just type cdtr or the first couple letters of whatever directory you want and hit tab and it'll auto-complete it. All right, so go into well, I'm going into trajectory. If I do ls, you'll see that I have these 2 files. One is this PRM top file and one is a DCD. These are just file extensions. I'm going to open up VMD using this. Sorry, what?
You can't do it on.
Oh, that's right. I'm on the
So
cluster.
don't, unless you're local, you're running it locally, don't follow his next commands. He's going to go over to the local computer and run this program that visualizes this trajectory.
Okay, so VMD is a visualization tool for molecular analysis.
You get the main, it's just.
Okay. So in that file, in the trajectory folder, in those 2 files, we have a series of coordinate data. And what I mean by coordinate data is it represents a molecule in 3 dimensions, but it also has data on the activity of that molecule over time. So so you can visualize it in one step at a time, or you can visualize it kind of in motion and see how it behaves over a period of. It's a very small period of time, but you can visualize certain behaviors.
No, move it to the left. Move that screen to the left.
Oh, there it is. Yeah. So what I mean by that is this. So I'm able to manipulate time a little bit so that I can see how this molecule behaves. And if I'm interested in its behavior at, say, the 91st time step, I'm able to rotate it and observe various things about it. Furthermore, if I say I'm interested in something more specific, like perhaps the distance between two specific hydrogen bonds in this molecule, I can go into BMD and I'm able to isolate those hydrogen bonds that I'm interested in, and it was in
Mouse.
oh right, mouse, yeah.
Label bonds.
Okay. And let's pick some here. Martin, correct me if I'm horribly off cue here, but
No, that one.
not that one. Yeah, maybe I'll have you show me this part. I'm a computer scientist, not a chemist, so.
Okay, so we're going to select, for example, this hydrogen bond distance, which if you can see right now is at 2.08, but over the trajectory it changes values. And what we want is to get that data set, that time trace of the distance of that particular hydrogen bond.
Right.
Now we go to labels, bonds. You can graph it, for example, and you get the time trace.
Right, so this is what those hydrogen bond distances look like over a period of time. And this is a simulation that was run on the cluster that you'll get into later in this course. Right, so
Right now, you're running EMD locally,
correct.
but the file you're running is up on the cluster, or did you download it?
I downloaded it from the, that's a good question. So I had a simulation that I was interested in, a system that I was interested in, and I configured it on the cluster to simulate this specific system. And then I ran this task, and it simulates this molecule over a period of time, and then saves all of that time-dependent data in a file, or a series of files, which I can then download. And after all the simulation is done, that's the computationally expensive part. So once I have that data done already, I can put it on a local machine, like Martin's laptop, and run it on BMD, and it lets me see what happens. Okay. So being able to export these kinds of files is very useful because, as I will show you now, we can use Python to glean certain kinds of insights from the results of these simulations. So I'm going to shrink this down and go back to my terminal. So if you're in the trajectory folder, then you have access to the files that I just visualized on BMD. BMD is, you can download it from the internet, and I encourage you to play with some of these data files and see what you're able to do. What I'm going to do is go into no array. So this is where you want to follow along with me again.
What's the objective
So with
that data set?
Well, yeah, so with this data set, what Martin showed is how you can take that simulation and output files of different kind. Well, you can output data that's related to the system that you're interested in. What I'm going to show you is how to take the data that you've output from VMD and manipulate it using Python. So for instance, if I have this So this hbond.dat file, for instance, is something that was generated by VMD after feeding a simulation to it and doing some kind of analysis, right?
Well, just exactly, almost exactly what we just did.
Right.
I exported an hbond1 or 2.dat file, just that distance I selected and saved. So you can view that hbond.dat file with VI. It's a text file.
Right. So that hydrogen bond distance that we just looked at, this is the result of doing that analysis. So this is the length of that distance over a period of time. So you can see that it changes as the molecule moves around. What we're interested in doing is using Python to perform some calculation that, in this case, we're interested in the standard deviation of that distance. So how much it moves around over a period of time. We're going to do this in a variety of ways so that you can see how Python can be flexible with different types of information, with different information structured in different ways. Let's say it that way. So, maybe the most introductory way to handle data in Python is without the use of any kind of arrays or lists, which I'll explain momentarily. If you open this hbond file, you'll look and see that it has an index number on the left and a bond length distance on the right. We're not going to change anything in this file. We're just going to use VI to open this average standard deviation.py file. And I'm not going to go through every line in this file, but I'll point out a few key things. First of all, is any of these lines that have this pound sign at the front that are blue, these are comments. These are not going to be interpreted by Python. These are for you to look at and to know what's going on with the code. Okay, so if at any point you get confused and you have this code to reference, you can look at these comments and it'll tell you. This code goes through those bond lengths and computes the standard deviation for that length of time, right? So I'm sorry, yeah, the average of the standard deviation. Average and standard deviation, okay. And it does that by using a for loop like we talked about with the Hello World program to iterate through those lines in that file, which I'll illustrate in a second. It iterates over the lines in that file and performs some computations, which I will show you down below. Okay, so where it says for line in F, up at the top it opens the file and it saves it as F, and then it just goes through and it reads, without explaining every single line, it reads those hydrogen bond lengths on the right side of your line, and it saves them in, it sums them up in this data sum. So every line it goes through and it takes another bond length and it adds it to this number. So at the end what you have is a sum of all your hydrogen bond lengths over time. It's just one hydrogen bond, but you're summing the distances that are measured for that bond over time. So what you end up at the end with is a number that, if you divide it by 10, you'll have the average, or the number of iterations that you've done, you'll have, the average, which is what we do here. If we want the average bond length for that length of time that we simulated, we have data sum, which is that number that we've just calculated using a for loop, and then we divide it by the number of lines so that we get the average. Is that clear? Did I too quick? Okay. And then we just use that print statement that we discussed earlier to print the value out. I believe the standard deviation is computed afterwards. Right, so we start with a value of 0.0, and we open the file up again. We iterate through it one more time, and we use the average that we computed before, as well as the individual bond length for each time step. So we get the difference between the actual bond length at a given time and the average bond length over the whole simulation, and we store it in this temporary variable. Okay, it's just simple arithmetic. It's not hard to read. This symbol is a little confusing. What this means is take the value that's already in data standard div, standard deviation variable. Take whatever's in it and add this value to it. So whatever's in there, just do this and add it on top. So temp times temp is just the same as temp squared. Temp is just that difference that I mentioned a second ago between the actual bond length and the average bond length. So we square that value and we add it to this. Does that make sense? Okay. F.close is a good practice to get into. If you ever try to write something to a file and you don't close it, it will not save what you do. And it won't tell you why that happens, so that's frustrating. Okay, so then at the end we just do, we use this math.sqrt is square root. So math is a library that's built into Python that contains code that you don't have to worry about. It just works for you. Square root does what you think it does. So we give it standard deviation over the line count to get the standard deviation per bond, and then we take the square root. Well, we take the square root to get the standard deviation. Okay, so all in all, we're just using time-dependent data to get data that encompasses the whole thing at once. Does that make sense?
Important things to notice here are that you have to open the file twice, same
Yes.
file twice.
Right, because
you have to do that because you're why?
Right, so we do that because we have to compute that sum first. In order to compute this data average, we have to go through the whole file once to get the sum. Then we compute the average. Then we can use that average in this calculation where we have to go through the file a second time. Does that make sense? Okay.
Strategically, is there a reason not to have just loaded the file into an array or something?
That's a good
so
question.
That you
I'm glad you
didn't
asked.
have to open it
Could
twice?
you run it?
Oh yeah, I'm sorry. That was. Oops. Okay, so you see that it sums those hydrogen bond distances. You get a really big number. Then you divide it by the number of those samples that you've collected, and you get an average. And then you use that average. You open your file again. You iterate through it, and you use the values again to compute the standard deviation. Okay.
The answer to your question, though, is because we wanted to illustrate that you can do it without moving. But the next examples will be exactly as
And I mean, I presume depending on how big your array, there's advantages.
Right, so in this way, you don't use, it's computationally intensive, memory completely non-intensive.
Right.
The other way is memory intensive, computationally non-intensive.
Right.
So depending on what your application is, or what your data set is, you might have to do it with no array, or you might want to do it with an array. It just depends.
Right. Okay, so if you want to follow along with me, I have backed out of the no array folder and I've gone into the array folder. Everybody with me? Okay, so I'm gonna use VI to open average standard deviation again. And I want to point your attention to this line, this data list. From where you're sitting, this might just look like a white box, but it's actually these, up here you see it's these square brackets. In Python, square brackets are typically indicative of something called an array, which you can think of as just a linear collection of things. The things that we're collecting in this instance are numbers. So we're going to use those to get around that issue where we had to open our file twice. Because with very large files that can introduce inefficiencies in your calculations that can make them take longer than they need to, and it's also much easier to re-reference numbers if you can just store them into memory. With really any computationally intensive calculation, you have to take into consideration how long it's going to run and how many resources you have to dedicate to it. So if you have infinite resources, you could just save everything in memory and just reference it from there all the time. But if you're trying to run everything off of just your laptop, you're not going to have the memory to store some kinds of files in your memory, so you're just going to have to sacrifice some time to do everything again. Anyway, I apologize for that tangent. What we're doing here with this array is we're using some memory to store that data so that we don't have to open the file again. So when we get into this loop, what we've done is typically in the last example, this is where we just read the value and we performed a calculation. What we're doing instead here is we're using datalist.append. So you see that we've taken this hbond distance from the file, from the hbond file, and we've done datalist.append. So what that does is in the computer's memory, it starts a collection of the values from that file. So once this file is closed in this line here, the program still has all those values in its memory, and you can perform calculations without ever having to open that file again. Okay, so so if you remember in the last one, we used that math library to have access to some math functions that were useful to us to not have to write out by hand. Another one that you're going to become very familiar with is it's called NumPy. The way you get to it is by, at the top of your code, you do import NumPy. And then this as NP, it just allows you to reference it as NP instead of having to type out NumPy every time. Okay, so what NumPy does is it gives you, it's like the math library that we used before, but it just has more to it. So in this case, we don't have to calculate the standard deviation and the mean by hand. We can just ask NumPy to do it, and it will. So NumPy really likes these array structures, which makes using them which implores you to use them more often. This as array is a NumPy function that you can call. It's just a piece of code inside NumPy that takes that array that we defined earlier with the square brackets, and it saves it in a way that NumPy can read efficiently. Okay, so this is just storing it in a way that NumPy likes, and then we can use numpy.std to calculate the standard deviation, and numpy.mean to calculate the mean. Okay, and then when we run it, Control C. So when we run it, it tells us, what we ask it to print out. The values are the same as last time. So, well, sorry.
That's important.
Yes, that's important to have consistent values when running these calculations on the same variables or same values. Shows that NumPy does what we say it does. So, okay. So is everybody still following along? Any questions? No. Great. Sorry.
I haven't got to this.
Say that one more time.
I haven't got to where you are right now.
You're not where I am?
No.
Where are you?
I tried to type in Python and then the average standard deviation. Try to run it.
Oh, yeah, so you might have been following what I did and I made a mistake at that part. So you'll want to do, yeah, you have to tell it what file to use. So push the letter F key. And I'll do a space and then hbond.f. Okay, so follow me now into this list folder. Okay, so when you open this version of the program in VI, you see that we have this data list structure again. We do the same thing where we append our values to the data list array. Okay, we close the file out, we compute our data average. In this case, we've done it manually. So with NumPy specifically, if you convert your data into an array using NumPy, then it's not. Then that's called an array. It works similarly to a list, which we're using here. But if you have a list in NumPy, they call it an array. If you use it outside of NumPy, it's called a list. But they're the same thing. They're just a collection of elements that you can access in order. Okay. So in this case, we're using this sum function to sum all the values in data list, which again is that collection of numbers from our hbond file. So where sum comes from is not from NumPy or from math, but from our own code, if I recall. Or is sum just a part of Python?
Sum is a part.
Okay, my mistake. Sum is just a sum just comes from Python, so you can use it. So we sum the data list and then we divide it by the number of lines in our file to get the average again. Print them out, and then to do our standard deviation, because we're not using NumPy, we're not using arrays, we're using lists here. So since we don't have NumPy, we're gonna compute it manually. Again, we just take those differences between the average and the distances and square them and sum them up in this variable. And at the end, we do use the math library to take the square root of this fraction, which gives us our standard deviation, okay?
So this one is more, you went out of, but this one is more like the first one, except for, because you're not using the NumPy libraries.
Yes.
But in this case, the difference between this and the first one is mainly that you don't reopen the file.
Right. In this one, you'll notice again that we don't reopen the file because we just save everything in a list. Again, that was one of the strengths of the array, was that we could just store things in memory. Same case here. One benefit to using the list. So you're probably wondering, well, if you can't use NumPy with lists, but you can with arrays, why not just use arrays all the time? With arrays, you always have to use numbers. You can't use, as far as I know, you can't use text or other crazy data structures. You just have to use like decimals and integers, pretty much what you're limited to. With lists, you can store text, you can store integers, you can store floating point values, you can store anything you want in there. And so it makes it handy in some cases, but in other cases you want NumPy because it's very efficient at what it does. Okay.
What's the difference between floating points and?
Oh, an integer? So, yeah, good
Well,
question.
I know an integer, but
Okay.
I thought you said you could use like an integer or just a number. So is that really only?
It's, well, without getting too into the weeds, computers, well, it's Python specifically, and in other computer languages, will store values as types of data.
Right.
So you'll have, with a floating point value, it takes no matter what the number is, it takes a certain amount of memory to store it.
Yeah.
And you can use different types of data to, if you want various levels of accuracy. So in some languages, they have a thing called a short, which I think gives you like 8 points after the decimal. Mm-hmm. With float, you get like 32, I think, and some you can go all the way up to 64 points past your decimal or something like that. So, it comes down to how much accuracy you need, how much space you have, and how accurate the data that you're given in the first place is. Okay, any other questions? Great, so we're going to get out of, where are we? We're going to get out of data set. We're going to go into benzene. This is in the day 1 folder. And then you want to go into the molecular geometry folder. Everybody there? Cool. So you'll notice in there you have a file called benzene XYZ. If you open that with VI, you'll see this. So this file gives you the coordinates for the XYZ coordinates, so think of three-dimensional space. You have a molecule, a benzene molecule. This gives you the coordinates of each of the atoms in that molecule in three-dimensional space. Okay, so you'll notice that in your, this is your X, your Y, and your Z, you'll notice that in your Z-axis, we don't have any change. It's just all essentially a two-dimensional, it's a benzene molecule, so it makes sense. But you have your carbons and your hydrogens listed out here and their respective X and Y coordinates. And then at the top, you have the total number of atoms and the name of your molecule. Okay? So nothing too mysterious about this.
How did you get that? How did you make that geometry?
Oh, this so this came from BMD, yeah.
No. Trigonometry.
Oh, you're saying oh, yeah. Okay, so
it's important to, there are a variety of ways to make or get the coordinates for a particular molecule into your XYZ formatted input file. The easiest way is to Google it and try to find coordinates for it. But in the case of a simple molecule like benzene, you can actually devise the coordinates of it by simple trigonometry, understanding some chemistry and trigonometry.
true. So if you're familiar with your hexagon-shaped benzene molecule, you can use trigonometry and your understanding of how these atoms bond together to let's open this again, to know the angles between these bonds, so that you can calculate these coordinates yourself. And what's handy about having these coordinates is that you can then apply mathematical transformations to them, so that you can, in a sense, you can physically move your molecule around in this virtual space.
That, by the way, that file is viewable in BMD. So if you want to, again, you can't run BMD from the cluster, but if you want to download that file and then locally run BMD on your laptop, you can view that file if you want.
If I were to do that, does it BMD?
No, turn.
Do you guys know how to move files from the cluster to your computer?
Yes.
I think that question was for somebody else in the room.
Yeah, so the other program that for people, you three, or actually four who are using PCs, I sent a link to two programs, PuTTY or some sort of thing like that, and WinSCP. Is that right? Did you guys download that other one? WinSCP is the program you will use to transfer files. The login information is the same. It would then pop up with two windows, one of which looks like files on your local machine, and the other is on the cluster. And then you can just drag and drop the files from one to the other. You have to move directories like you would in a Windows Explorer thing, and then transfer files. So on a Mac and a Linux machine, you can use if you want to go through that. I think everyone who has a Mac or Windows machine knows how to do that. Or not. Bridget, do you know how to do that?
You can remind
Yeah,
us.
I can show you later. But for now, we don't need to do that, but probably you'll need to do it this afternoon, so play around with it. If you can't figure it out, find Greg, myself, or Gary. Okay?
Do you know how to use like SCP?
It's been a while.
I can show you.
It'll be a 30-second
Sure.
tour. I just have to stop.
Yeah. Okay, so go ahead and just go to your local machine and go to that folder and
Just that. Okay, so we see a benzene molecule here. It's flat, just like we expected. There's no time data here, so if we move this, it's not going to do anything. But we see we have 12 atoms, so we can visualize it, and we see that it's shaped the way it should be. So
you could manually edit that file. For example, go into the molecular geometry, put it on locally,
oh yeah.
and go, and edit one of the z coordinates.
Now you'll see we have this one carbon that's way out there. Okay, so it's pretty easy to edit these things, which is handy because that's what we're about to do. Okay, so if you're in this benzene folder, which I hope everybody is, what we're going to do now is go into rotation. Is that the next one? Okay.
You can do whatever you want.
All right, so we're going to go into rotation. As you might guess, what we're going to do is use Python to rotate this molecule. Okay, so we're just going to use some mathematical transformations on those coordinates in our file, and we're just going to rotate it a little bit. So if I go into VI and open this rotate XYZ, we're going to look at what this does real quickly. So first we have these variables pi and deg to rad, or degrees to radians, so that we can do some trigonometric transformations. And then this is important up here. So I told you guys about this comment thing. This def means that this is a definition for a function, and a function is a piece of code that you can call to whenever you want to, and it'll do some set list of things. So that set list of things is, remember our tabs earlier? You have to tab when you define a new function. So this read XYZ function, everything that's tabbed forward under this def line is part of this function. So whenever I call read XYZ, it's going to do all of these things up until here. Okay. So read XYZ, like this comment says, it just takes an XYZ file and it reads the values in, and it uses this list structure that we talked about earlier to store our values in memory. Okay, so you can look at the comments and they'll tell you what each little group of lines does, but ultimately it takes that benzene XYZ and it just saves it in memory. Okay, so then we have another function defined here called write XYZ. It takes a positions argument, which you just have to provide these values when you use this function, and it'll use them appropriately. So it computes the number of atoms in your file, and it basically just writes out a brand new XYZ file, just like the one I showed you guys a second ago. So what do you do between reading and writing? Well, you perform this transformation. So you've read in this XYZ file, you've got your coordinates in your memory now. Now what we want to do is rotate it by a fixed amount. So we're going to use these coordinates, and we're going to use some trigonometry. So we define this theta value when we see up here. It says positions comma theta. So when we use this function, rotate y, we give it a positions, which is that list of our initial coordinates, and then we give it a theta value, which is the angle that we're trying to rotate by. Okay, so
Degrees or radians?
I'm sorry? Oh, it's in radians. So at the beginning when we give it pi and we give it deg to rad, and it uses pi to convert to radians.
Yes, so internally it uses radians, but the input from the user in this case, which will be the angle, is in degrees, and then we just convert it to radians internal to the code, and then these math routines take theta as radians, essentially.
Correct. Okay, so here we're using NumPy to define getting into it a little bit, but we initialize this with a bunch of zeros, and then we go through and we set each of those zeros to something new in these next couple lines, you just, we take the cosine and sine of this angle value so that we rotate each of the points by the correct amount. And then we define the new positions by using the dot product of these trigonometric rotation values and our initial position values from our file, okay? So we take the dot product and we save it in a new variable called positions. And then our function just returns that positions list. So that's our coordinates after we've applied this rotation function to it, which is what we're looking for. We have a similar thing for z, and we should have another. Maybe x was up above. And then this code down here is what actually it's a little confusing to think of it, but it's what runs first because those functions that we defined at the top, those def lines, that means you can call it anywhere you want, but it does not say when or where that happens. So all that tells the computer is that they exist. They're not actually being run. What starts being run is this, see it's in comments over there, it's this main program here. So where there's no def, that's the code that the computer is going to run initially when you start your script. Okay, so it's just going to take these inputs from the user. It'll compute the radians. It'll take your input, which is degrees, your rotation angle, which is in degrees, and it'll convert it to radians. And then it just performs these calculations that we defined earlier. So instead of all that code that we saw in those functions, it's reduced to just this one line, rotate x, rotate y, rotate z, and then it writes them out to a new file, okay? Was that too fast for anybody? Anything
Just go through the system arguments really fast, 1, 2, and 3.
Okay, so.
Which is 1, which is 2, which is 3.
Okay, so when I do Python benzene XYZ, anything I put after that is an argument to this program. Okay, so the first thing after benzene XYZ is going to be argument number 1. The next thing after that is going to be argument number 2. The next thing after that is argument number 3. So what that looks like. Well, right here it references these arguments. The first one is going to be your input file. Your second one is going to be your output file, and your third one is going to be your angle. So you have to adhere to that when you supply these commands. If you put them in the wrong order, it's not going to work correctly. And what's worth paying particular attention to is if you put your output file where your input file should be, it can overwrite your input file and you can lose data. So you have to be careful with that. Okay, so in the spirit of that, I'm going to put my input file first. Okay, so Python rotate XYZ, and then, oh, I'm sorry, I think I misspoke earlier, but so you just follow with what I do, and I'll illustrate it. So my input file is my first argument, right? So my benzene, I'll call it rotate 60.xyz, and then I'll just say 60 is my argument. Okay, so I'm rotating my benzene molecule 60 degrees, and I'm saving it in a file called benzene rot60.xyz. Okay, so when I run it, it's going to take a second. It's going to perform the calculations that I've asked for. I think. Sometimes when you run Python scripts on the cluster, if the cluster is doing a lot in the background, it can take some time to run your scripts. There we go. Okay, so if I use VI to open this benzene XYZ, now we see that I have a translated molecule with new coordinates, including some flashy new Z coordinates.
It shouldn't be translated. So
Translated.
printed translated, but it should have really been translated.
Yeah, it should have been rotated here. That's just a typo in the code, yeah. Okay,
Show where the typo is.
Benzene. Oops, that's not. So what it should have been is, let's see if I can find it here.
Search for translate.
We've gone through the search functions.
Yeah. No, actually, I use VI so infrequently I don't actually remember how to use the search in VI.
Slash.
It's right. Remove slash right XYZ.
Slash.
Right. Just search for right XYZ. It's upside down.
Oh, okay, yeah.
Okay, next one, M.
Just hit select.
There it is.
There it is. So here, so this code is supposed to rotate it, and we just want to change this so that it says rotated molecule. I won't run it again, but that's where that came from. So if we go now into, okay, first thing, any questions? You rotate them. Let me,
Yeah, it's got 10 minutes.
okay, 10 minutes, all right. What we're going to do now is go into translation. All right. So when we perform a translation, instead of rotating a molecule about an axis, all we're doing is moving it a fixed amount of space. Okay. So we have our benzene XYZ. In this case, we read in our XYZ again. Same function as last time. We have another one to write it out. This one says translated, which is right. The same arguments as before, input, output, and then the distance by which you want to shift your molecule. Okay. And then here, all we're doing is we're taking this atom positions, which is our list of all our coordinates, and we're just, remember this plus equals thing means take what you have already and just add this value to it. So this shift value is what you're providing as an argument. So if I say that I want to shift it by 10 angstroms, then it'll take every atom in my molecule and it'll shift it by the same amount in the same direction. So let's see what that does. That was much faster. Okay, and now you see we have the same molecule, but all of our coordinates have been incremented by 10. Okay. Okay, so with that, you can imagine now that you can take these rotation computations and these translation computations, and you might be able to combine them. Okay, so with rotation with rand, I believe what that does is it's just by a random angle. So with rotation with rand, I realize we're down to our last few minutes. Rotation with rand allows you to rotate your molecule by just a random angle, and translation multiple. If I remember, it lets you translate multiple molecules at a time by that fixed distance again. So how is this useful? Well, if you're trying to study a system, you might find it interesting to rotate your system so that you could find some shape or structural information about your molecule. And being able to move molecules closer together, as you'll see later in this course, sometimes it's of particular interest to put molecules in a certain position before you start a simulation, so that their energies interact in certain ways. And that's all stuff you'll get into further into this course, but the core of it all is going to be based on these scripts that you use in Python. And what you're going to do for your project later this afternoon is to do something very similar to what we've shown in these last few scripts. I believe you're going to create a system with multiple benzenes in it that you're then going to, later on, when you're learning how to submit simulations to your cluster, you're going to use those systems that you set up today. Okay, so
the project is to take the geometry, in molecular geometry, take that single benzene molecule geometry and create a box, so an XYZ file with multiple copies of benzene distributed throughout a box and randomly oriented. So instead of them stacking like a perfect crystal, for example, in exactly the right flat orientations, you want them randomly oriented relative to each other. Okay, so that's your objective with project today. My hint is that you're going to combine that translation multiple, so that although you haven't gone through it, what that translation multiple does is basically create a grid of a perfect crystal. So it just takes your benzenes and creates a grid of them all stacked nicely oriented. Then you can combine that with a random rotation of each molecule independently. So that would be those codes Greg has not gone through, but the underlying, besides the random number generator for the angle, the underlying code is exactly the same as the translation and rotation code that we just went through. So what I would suggest to you guys is play around with that translation multiple, play around with rotation with rand, and then try to go through it and understand what each step is doing, and then attempt to combine them. And if you run into roadblocks along the way, feel free to ask Greg or me or Eric or anybody else around.
I work in Martin's lab pretty much every day, so at least until the end of June, so come find me.
And these 4 of you will be situated in my student office for potentially longer than the 2 weeks, but for these 2 weeks. So my student office, which is C117, is a good place to potentially do some troubleshooting and working in groups.
Okay, any burning questions about Python or Linux or anything that we've gone over so far?
With Python, is it a blank line that ends the do loop or the if then?
It's just when you stop tabbing things.
Okay.
So when your first line that's all the way to the left is the end of your loop. Or I guess more accurately, it's the first thing after your loop is ended.
But for some reason, my clock is wrong here. There's another 15 minutes. But people are, I think that it's probably a little overwhelming on the first day anyways.
Yeah.
So people can take some time to digest it themselves and come ask questions would probably be the best way to go about it.
Yeah, thank you very much.